In this video, you will learn the final type of machine learning model on PA, the tree-based model. Broadly, this is called the Decision Trees chapter, but it actually refers to 3 different types of models. You'll learn how to understand the basic motivation behind decision trees, how to construct regression and classification trees, bagging and random forests to improve accuracy. Along the way, you'll learn how to select appropriate hyperparameters for each of these models. So what topics do you really need to study? Well, let's review the different types of models that we have on this exam. The most common is the 𝐵LM. This appears on every single version of exam PA. Let's review the different types of models that you will need to study. As you can see, some of these models appear much more frequently than others. Each row of this table is in a sitting of the exam, going back to 2019. You can see that every version of this exam has contained a 𝐵LM as well as a decision tree. There are some variations. Sometimes you use stepwise selection with the 𝐵LM, and sometimes you use regularized regression. Bagging and boosting, or random forests and GBMs, have only appeared in December of 2019 and on June 13th of 2019. So if you need to focus on topics, first learn the 𝐵LM and the decision tree. In order to fit these models, various parameters need to be chosen. You already know about training and test splitting. This is when you use part of the data for building the model and then the remaining part for evaluating the performance of the model. On your executive summary, you'll need to always include a paragraph that says something to the effect of this. For instance, after modifying a few features to prepare them for modeling, I tried a variety of models to see which would best explain the factors affecting the length of hospital stays. Each model was calibrated using 70% of the data, the training portion, and then measured using the other 30%, which is the testing. This process helps identify models that adequately capture the pattern of data and generalize well to new data. One way of choosing hyperparameters is known as the bootstrap. This is a way of making your data larger. This works by resampling the same data, except you use replacement, which means that it's possible for observations to be sampled multiple times. So in this example, you're predicting a claim amount. You're using 2 predictive variables, and you have the target variable, which is y. And for some of these cases, the claims may be quite high. For these 2 observations, for instance. So your first bootstrapped sample uses A twice and B twice. And so the average claim amount would be somewhere between 1,000 and 20. The next bootstrap sample uses only claims C and D. And so this would have a higher claim amount. So you can repeat this process up to hundreds of times, where you would have additional bootstrap samples of the data. If you're fitting a linear model, you would then have different parameters for each model. So the model based on this first data set might have a lower average claim amount than, say, this model. So why do you do this? Well, remember that your goal is to estimate the beta parameters. So each time you run a bootstrap sample, you calculate an estimate for the random variable beta. Now remember that random variables always have a distribution. That is, their precise value is unknown and it can change. So each time you run a bootstrapped sample and fit a model, you generate one of these random variables. So there's a distribution for beta 0 and beta 1 and beta 3 and so forth. This allows you to then do things such as calculate the average for each parameter. So this would be the intercept term from the first model, this is the intercept term from the second model, and so forth. You can also calculate confidence intervals because you have a sampling distribution. Even if you don't know the shape of the distribution, you can do this empirically. It's very unlikely that these parameters would follow a normal distribution. They might be much more irregular. This is just an illustrative picture. The most durable way of choosing parameters is known as cross-validation. So as you know, you divide data up into train and test. The most durable way of choosing parameters is known as cross-validation. So you can divide data up into training or testing in multiple ways. You could just choose the top 80% of the records as the training and then the bottom 20% as the testing. Or you could choose the middle 20% as the testing set. Or you could choose the top 20%. When you do this, you'll get some variability. Just imagine that if you're predicting something like a claim amount, you might have catastrophic claims that only occur in the first 100 lines of your data. And so when you train your model with these in the training set, you'll get much different results than if you don't include them in the training set. The way around this is known as cross-validation. So this picture shows a partition of the data set, or rather, each row here represents the data. So this is 80% train, and then this here is 20% test. So you could use this first fifth of the data as your test set, and then the remaining 4/5 as the training set, or you could use the second fifth as the test set and the other 4/5 as the training, and so forth. And you do this k times. So this picture has 5 partitions. So this is 5-fold because the data is folded 5 times. So for each of these, you would get a model. So in the case of linear regression, you get parameters beta 0, beta 1, beta 2, and so forth. But if you were using a different model like a decision tree, you would get different parameters. So as you'll see in the next section, decision trees actually contain parameters. And so each time you train your model on different segments, you'll get slightly different decision trees. So finally, you then take the average over all of the folds. And this gives you a very reliable estimate of your parameters. Because if you were to repeat this process again, all of the randomness will be sort of ironed out through this mechanical process. Let's review the topic of decision trees. There are already many illustrations of decision trees available on the internet. So this will just be a simple explanation to get you the bare essentials for PA. I suggest that you also review Module 7, the study guide, the StatQuest videos, as well as ISLR Chapter 8 for additional details. Here's an example. You're predicting either a positive class or a negative class. The positive class is if the claim is above $20,000, and the negative class is if the claim is below $20,000. You are using patient information, their age, and their body mass index. So each of these represents a point. This person is a high cost claim, as well as this person. And this negative class here, this is a person who has a claim less than $20,000. So your goal is to divide up all of the patients so that you separate out the people who are above 20,000 from below. So you could just create a single rule that says if your age is below 20, then you are high cost, and if you're above 20, then you're low cost. This is what a decision tree tries to do. So it asks, is your age less than 20? Then it asks another question, is your BMI less than 15? So this divides the feature space into 3 regions. This is a partition. And then for each region, you say that the person's probability of being in the positive class is simply the percentage of records in that region which are positive. So let's look at region 1 here. Region 1 has 1, 2, 3, 4, 5 total people, and 4 of them are positive. So the probability of being positive if you're in region 1 is 4 out of 5. And the way that we got this was just by asking people if they were under age 20. Similarly, for region 2, there were only 3 people and all of them were positive. That's this upper right region. So you ask people 2 questions. Are you under age 20 and is your BMI less than 15? Trees have very clever terminology. Just like a real tree, except being upside down. Decision trees start with the root and then they go down branches. The height of the tree, also called the depth, is the number of nodes. A node is simply a split point. The final nodes are called leaf nodes or terminal nodes. Here's a practice exercise for you. Get out a piece of paper and draw this decision tree. Then for each of these 3 cases, decide where they would end up. Which terminal node would they go? This is from the SRM practice exam. Resume the video and we'll see if we can get the same answer. So the question is, the regression tree shown below was produced from a data set of auto claim payments. Age category, age cat, and vehicle age are both predictive variables, and the log of claim amount is the dependent variable. So this is Y. So the first question is age cat greater than 1.5? So they go right. So I should say, no, they go under this branch because age cat is less than 1.5. The second person is in category 5. So their age category is above 1.5. So they go left. And then their vehicle age is 5. So that puts them over here. And they end up with a predicted value of 8.028. Same logic applies for the third group. And notice that the N here is just the number of observations or the number of vehicles which fall into that category. So how do you decide where to split? Well, you could choose this split point right here. This is about age. So let's say this is between 10 and 20. This might be a value of age is equal to 15. But how do you know, is this a good point or a bad split point? So this results in 2 cases that are positive, 1, 2, and 2 cases that are negative. And then this region on the left has 3 cases that are negative, and it has 4 cases that are positive. But what if we chose a different split? Like what if we chose this split right here? Now intuitively, you would say that this looks better because it groups all of these observations together. So this results in a partition of 1 negative and 4 positives, and 4 negatives and 2 positives. There are 3 different ways that you could decide how to split, but only 2 of them are ever going to be used. So these infrequently appear on PA. You will need to know at least the definitions, and you'll need to know that neither of these methods work on all data sets, and so it's best to try out both and then compare. So it's possible that on PA you could get a question where they ask you to compute a very simple value such as this, or they ask you for a statistical definition where you'd have to type out a response. So classification error does not get used because it is not sensitive enough for determining if a split is better than another split. Now it's worth noting that these words, entropy and Gini, have never even appeared on exam PA before, but you can't use that as an indicator for future exams because quite frequently PA likes to include new topics. The first way to decide is using Gini, and you've seen some examples before in the modules where they ask you to calculate the Gini coefficients. So this will just be a quick review. So Gini ranges between 0 and 1. When Gini is 0, it's the best possible split. This is also called the highest node purity, where all elements belong to a single class. And Gini is equal to 1 is the worst split, or the lowest purity. Elements are randomly distributed across the classes. So let's look at the first split. So that is this split right here. So we're looking at this region. And so this is the frequency table. So the P, the probability being the positive class, is simply 4 over 4 plus 3, or 4 over 7, which is 0.57. So Gini is just 1 minus 0.57 squared plus the complement squared, which is 0.49. And likewise, for the region on the right, the Gini comes out to be 0.5. Now let's review the second split, which we knew was better. So this has a P of 0.8 and a P of 0.33. You calculate these Gini values, you get 0.32 and 0.44. Now to get an overall Gini for both splits, you simply take the weighted average, where the weights are the number of observations that are in that region. So the first region had 1 plus 4, or 5 observations, and the second had 4 plus 2, or 6. So the weighted Gini comes out to be 0.39. So in the first case, the weighted Gini was 0.49. In the second case, it was 0.39. And recall that 0 was best and 1 was worst. So this Gini, which is lower, is better. And that agrees with your intuition just by looking at this picture because all 4 of these records get grouped together, as well as these 4. The other method of choosing a split is called entropy. So entropy uses a log and base 2, and it's Fairly simple. So the formula is you take -1 times p times log base 2 of p minus the complement probability. So for the first case, you calculate p to be 0.8, and then the entropy is minus 0.8 times log base 2 of 0.8 minus the complement. So minus 0.2 times log base 2, 0.2, etc. And so this calculates different values. So the final tree parameter that we're going to talk about is the complexity parameter. This is called the CP. And so this looks rather complicated, but when you pull back the details, you'll see that it's actually very straightforward. So the first part looks over all the terminal nodes. So if you had a decision tree like this, it had 1, 2, 3 terminal nodes. And so you'd say this value of t would be equal to 3. And so for each of these nodes, you calculate y minus the expected value of y squared. But you've seen that before, right? That's just the squared error. That's just, y hat minus like actual y squared. So y hat I minus yi, and then you add to it alpha times the number of nodes, which is 3. Where have you seen this before? Well, what about with ridge regression? So recall, with ridge regression, you took the SSE, the sum of the squared errors, and then you added the value lambda times the square of the coefficients. So this was the loss, and then you add the penalty terms. So here's a tree before you use pruning. And as you can see, there are some nodes down here towards the bottom, which are far more specific than are necessary. And so when you use complexity pruning, you look at the value of CP for all of these subtrees, and then you choose the CP that has a desired value. So consider the first subtree. It just has 2 nodes. It's just asking people, is CA less than 0.5 or is CA greater than 0.5? So this would have a given CP value, call it CP1. So consider this tree, which as you can see is very complicated. You can use cost complexity pruning to make it simpler. So first of all, look at the top tree. This just has 2 nodes, and the CP value we'll just call CP1. And then you can compare this with the second tree. The second subtree would include this first node and then also these other nodes. And this would have a CP value of CP2. So you can repeat this process and look at different subtrees in their related CP values. So then you decide on what you want your minimum CP value to be, and then delete all of the nodes that come after that. So in this case, you can see that all of these nodes down here and over here and over here get trimmed off. This is an example of the bias-variance-tradeoff. Consider how a decision tree is related to the ridge or lasso model that you've already seen. As you move to the right, you decrease the model's complexity. This means that there's less overfitting, there's higher bias, and there's lower variance. For a single tree, you do this by adjusting the CP parameter. For the lasso or ridge model, you adjust the lambda value. As you move to the left, you have a more complex model. There's more overfitting, there's lower bias, and there's higher variance. Notice that the y-axis on these 2 graphs are different, but that's okay. The top graph is showing the relative error, which could be the misclassification error for a categorical model. And the bottom is showing the mean squared error, which is actually a regression metric. But if this were also from a classification problem, then the error on the y-axis would actually just be misclassification error. So what are the advantages and disadvantages? Frequently on PA, you'll need to choose between different models, and then you will need to justify your results. So it's helpful to memorize this list. The advantages are it's easy to interpret, performs variable selection, and categorical variables do not require binarization in order for each level to be used as a separate predictor. Here's an example of what that looks like. Let's say that you have a predictor variable, x, that can take on 3 levels, A, B, or C. Your decision tree can simply ask, is x in A and C? And if yes, move on to this branch. And if no, move on to another branch. So this is a way of specifically asking, is x equal to A or x equal to C? If you were to do this with a linear model, you'd have to create different dummy variables. One that would be is x equal to a, and then one for is x equal to c. And then this would be 1 when x is equal to a and 0 elsewhere. And this variable would be 0 when x is not equal to c and 1 elsewhere. And so you have to add these dummy variables to your matrix. But for decision trees, it does this automatically. Trees capture nonlinearities and interaction effects. So nonlinearities are obvious because the tree directly partitions the sample space. Interaction effects occur because the impact that each variable has depends on the other variables that are in the model. Take, for example, these two variables, age_cat and vehicle age. If your age category is greater than 1.5, then there's a different impact, vehicle age, than if your age_cat is less than 1.5, in which case vehicle age has no impact. So this would be similar to having a linear model where you have age_cat interacting with vehicle age. Just remember the definition. An interaction is when the impact that a predictive variable has on the response is different depending on the values of another predictor that's in the model. Decision trees can also handle missing values. The way that they do this is by creating separate branches for the NA values. So let's say I was observing an NA record for max HR. So that is to say the value of A was valid, the value of CA was valid, but the value of max NA was missing. Your tree could simply create another split and then make a prediction for that group. The disadvantages are that they do not have the same level of predictive accuracy as other models that you'll see on PA, namely the GLMs, Lasso, GBM, and Random Forest. They are often a simplification of the underlying process because all observations at terminal nodes have to have an equal predicted value. This is just saying that because your predicted values are discrete, often your performance is not that great. They can be very non-robust, meaning that changes in the data can cause a large change in the final estimated tree. You'll see this from experimentation. Your trees may look like they're making the problem a lot simpler, but when you change the data even a small amount, this can have big impacts on training. So you might spend a lot of time writing up a very detailed explanation of a tree, only to change the data and find out that that entire explanation is different. This occurs in real life as well. Here's an example from June 16. You can see that this question has a lot of different parts to it. It has 5 bullet points. Be careful to answer these questions exactly as they request you to. There are a lot of tangents that you can go off on when answering these questions, but you will simply run out of time if you don't follow the script. The first question was, describe what pruning does and why it might be considered for this business problem. You basically had to memorize the definition for pruning and then type it out. The next part was to construct an unpruned regression tree using the code. You didn't need to make any changes, you simply pressed run. You then had to review the complexity parameter table and plot for this tree, and then choose the optimal value. So here's the first part. You simply ran the code that created the tree. Notice the CP value was 0.001, which is relatively low. And so this results in a very complex tree. The height of this tree is 8. And then you looked at the plot here of the CP parameter. On the y-axis, you see the misclassification error, and on the x-axis, CP. You can see that when the CP is 0, the tree has the worst error, meaning that it's just randomly guessing. So this, as you increase the CP, you add more splits, and therefore you decrease the relative error. You can keep making the tree more and more complex, but your error will not continue to decrease. It basically flattens out. And so you want to choose a value of CP that is reasonable so that your tree is still interpretable, but your error is also low. Here's the table that outputs. So the first column here shows CP. Then there's the number of splits in the tree, the relative error, and the error. So notice that this X error column is just the misclassification error, and then relative error is just that normalized, so that the lowest value has a value of 1. So you just divide this column by the lowest value in that column to get to this column. And then the final column here is the X standard deviation. So this was prune the tree using a complexity parameter that will result in 8 leaves. If 8 is not a possible option, select the largest number less than 8 that is possible. So you simply had to try out different values of CP, try out the different values here, and then find the one that had 8 leaves or 8 terminal nodes. And that's what this looked like here. So you can count the number of leaves: 1, 2, 3, 4, 5, 6, 7, 8. So you next need to interpret this tree. This works by first asking, does the patient have fewer than 20 medications? If yes, that represents 73% of the data. The average value of the target is 3.7. Then it asks, is the number of meds less than or equal to 14? If yes, then the predicted value is 3.2. And then it asks, is the number of meds less than 8.5? And if yes, the value is 2.6. So the logic here is nummeds less than 20? Is nummeds less than 14? Is nummeds less than 8.5? And is nummeds less than 8.5? So obviously, if nummeds is less than 8.5, then it's also less than 20. So the final predicted value for this branch is 2.6, and this represents 15% of the patient. You follow a similar logic for all of the other branches, and then add that into the document. The next model that we're going to look at is called bagging, or a random forest. The next type of model that we're going to look at is called a random forest. This is also called a bagged tree model. As the name implies, random forests are made up of multiple trees. So here's an example of an ensemble model. There are 2 different decision trees, and they both work together. The tree on the left takes into account the person's age and their gender, and the tree on the right asks if they use the computer daily. Then it groups each of the people based on the answers. For each of the terminal nodes, it either increases or decreases their predicted value. So the tree on the left here, this adds 2 points if the person's under age 15 and male, and it adds 0.1 points if they're under age 15 and female, and so forth. And then the tree on this right here, it asks if they use the computer daily, and if yes, it adds 0.9. So then the final prediction for a given example is the sum of the predictions for each tree. Now remember, random forests are not that likely to appear. If they do appear, they will likely to ask for the definition of bagging. So bagging is when you take the results of multiple trees and you add the predicted values together and then divide by the number of trees. Your final prediction is an average. This stands for bootstrapped aggregation. So each of your trees is fit on a different bootstrapped sample of the data. And what this does is it causes your trees to be somewhat independent of each other. You can think of this as that they are IID, or independent and identically distributed. Why is this the case? Well, remember that the different bootstrapped samples of the data use different observations. So let's say that this first sample used a lot of cases from A and B claims, but the second used a lot of cases from C and D claims. These will fit different decision trees. The first one will maybe predict a value that's between 1,020, and the second will predict a value that's between 500 and 2,000. And then when you average all of those together, you get a result that's even more generalized. Why does the performance improve? Why not just use a single tree? The answer is actually because of the bias-variance-tradeoff. Bagging reduces the variance while retaining the bias. Now you know that as you increase the sample size of something, you decrease the variance of that thing. The bias-variance-tradeoff looks at the variance of the estimated model. This is how the model changes as the data changes. And when you fit a decision a random forest that uses hundreds of different trees, the results do not change very often because averages are stable. The bias, however, stays about the same because the structure of the model isn't changing. For classification, trees work by what's called majority voting. So this picture shows 3 different trees from your random forest. The first will send the person, so let's say that you are given an observation. Each tree will then classify this observation. The first might send it down all the way to the far right node down here and give a certain predicted value. The second might send it down to the second most node. The third tree might send it down a different node entirely. And each of these will predict different classes. The first tree may say, this is class A. The second will say this is class B. And the third might say it's also class B. So the final class is then related to each of these predicted values. So in this case, let's say that you are predicting P is equal to the probability of getting class B. Then this would be P is equal to 2/3, because 2/3 of the trees are saying that it's B. Now, in reality, you would typically use hundreds of these trees. So then your final predicted class is actually a probability. And so you get the probability by saying, is P less than some cutoff value? And this cutoff, you have to tune experimentally. The default cutoff is 0.5. This is for majority voting. So it says if your probability of being in that class is greater than half, then use that class. But you could also change your cutoff to something like 0.1 or 0.2 or even 0.9, depending on your problem. Partial dependence is a tool that lets you measure the impact that X has on the target after integrating out the effect of all other predictors in the model. This has never yet appeared on PA, but it works quite simply. You first consider the model. Let's call this F, which is a function of x1 and x2. You then look at the training data. For each occurrence of x1 and 2, you have the predicted value. But to get the partial dependence, you need to consider all possible combinations of x1 and 2. And then you evaluate your function at these values. So then to get your partial dependence, you consider the marginal average. So take the example where x1 is equal to 1. You have 3 occurrences. x1 is 1, x2 is 3, x1 is 1, x2 is 4, and so forth. And so then you just take the average of those 3 values. And you also do this when x1 is equal to 2. So then your predicted value just comes out to be 36. So here's a graph. On the x-axis, you see the predictor age, and on the y-axis, you see the target. So you can see that the target increases as age increases. This can be very misleading for high-dimensional problems, where you have a lot of other predictor variables because you don't consider the interactions. Advantages: resilient to overfitting due to bagging, measures variable importance, and all the benefits of using single trees. There's only one parameter to tune, which is mtry. This is the number of features considered at each split. There's another parameter called nTrees, which is the number of bagged trees, but you often don't have to tune this. This is because if you look at the graph, you'll see that the error flattens out once you get a value of nTrees that is high enough. The disadvantages are it's more difficult to interpret than a single tree because the results depend on many different trees. They often require over or undersampling when the target is an imbalanced class. This video hasn't talked about that, but this is when there are many more positive examples than negative examples. Think of modeling loan defaults, where 99% of loans might never go into default, and so you don't have enough positive examples to learn from. Random forests don't work well with this type of data, and so you need to use a stratified sampling method to counteract. They also tend to have lower predictive power than boosted trees, and they are unable to predict beyond the range of the training data for regression. The final model that we'll talk about is the boosted tree. This takes the target and then subtracts the mean of the target. It calls this T1 and then says T2 is equal to T1 minus the predicted value of T1. How does it make this prediction? Well, it's called a boosted tree, and so naturally it uses a tree. Now, technically, you can also use boosting with other types of models. You can use linear boosted models, but in this case, we're just looking at trees. Then T3 is equal to T2 minus the predicted T2. Your boosted prediction is then the sum of these values. There are two parameters: the boosting parameters, which is how all of the trees should be combined, and the tree parameters, which tell how each individual tree should be fit. The boosting parameters are things like the learning rate, which is how quickly each tree's contributions get combined together, the number of trees, and the fraction of observations that you use in each tree. And then the tree parameters are what you are already familiar with from working with single trees. Notice that you don't need to remember any of these because you can always look at the documentation in the RStudio environment by just typing in $GBM or $random forest. The advantages are that they have high prediction accuracy, higher than any other model exam. GBMs have been shown to work empirically well on many types of problems. In Kaggle, which is a competitive machine learning website, a GBM is almost always used in the winning solution. Actuaries use GBMs for a wide variety of problems. They detect nonlinearities, interactions, resilient to outliers, correct for missing values, and so forth. The disadvantages are that they require a larger sample size than a GLM, they require longer training time, and they are quite easy to overfit. This is because there are a lot of different parameters to tune, and it can require a lot of extensive cross-validation or a lot of training data to test out different versions of the model to find the best set of parameters. Finally, here's an example. Consider a boosted tree. Do not construct a boosted tree. Describe both the random forest and a boosted tree and explain the similarities and differences. This was from December of 2019. Notice that it doesn't ask you to do any coding or to do any complex math. You simply have to write out an explanation like this. See that there are paragraphs that basically highlight the different facts about the model. So if you just remember these facts by looking at our cheat sheets, you will be well prepared.